Ah, I'm still not seeing anything.
You're transmitting now. Let me
Yeah.
check.
Oh no, it's okay. Yeah. I cannot see it, but the audience can see, so that's cool.
Oh, they see?
Yes, they see. At least in the transmission, yeah, it's everything is going well. So it's not yet on the platform, but I'm just doing some alterations here. So. I'll just do a quick introduction, and then you can start.
Let me ask you, what about my background? My background is flippy or is correct?
Your background is flipped.
Yeah, it's
flipped.
yeah.
What about now?
Still flipped.
Still flipped?
Yeah.
What about now? No?
Yes, I don't think there's a change.
Okay.
Let me see.
Now it's correct, yes.
Now it's correct?
Yeah, now it's correct.
Okay.
Okay, so I'm sending my colleague the link, and he'll let me know as soon as we're live on the platform.
Oh, meu Deus. Quem que tá aqui? O que que aconteceu?
What about my background? Is it flipped or not?
No, it's correct. No, it's correct. And
No, it's correct. Okay.
I'm seeing the presentation clearly, so I think
Okay.
it's operational now.
Your background, when you got in, the post-tech part was on the it was
Yes,
like,
yes.
Pode-me chamar ali no Jitsi e estamos a ouvir tudo.
Okay, I think.
Ok, acho que já estás a transmitir, Catarina. Yeah.
Okay, they're asking me to wait just a little bit more.
Não precisas de mim. Mais pena.
No, tá tudo bem. Obrigada.
Goodbye, Professor. I'll leave you to the Katerina. You're in good hands.
So participants, the presentation should last 40 to 45 minutes, and then the participants will ask some questions, and I'll put you in the end. Okay, so good morning, everyone. I am very pleased to present Dr. Chul-Hong Kim that joins us from Pohang in South Korea. Dr. Kim studied for his PhD degree and postdoc training at Washington University in St. Louis. He currently holds a Muenjai, correct me if I mispronounce it, Dr. Kim,
Yeah, that sounds great.
chair professorship at Pohang University of Science and Technology. He is the director of the Medical Device Innovation Center at the same university. And besides all that, he's also the CEO of Optico Inc., a spin-off company that commercializes preclinical and clinical photoacoustic imaging systems. Recipient of numerous Achievements Awards. He joins us today as an MBS Distinguished Lecturer to talk more about trans-energy multimodal imaging from development to commercial products via clinical translation. Thank you, Dr. Kim. The stage is yours.
All right. Thank you for kind introduction, and it's my great honor to share our recent research progress with you guys. So my name is Chul-Hong Kim. I'm professor of electrical engineering at Pohang University in Science and Technology. So today I'm going to talk about multimodal imaging from idea to commercial product. So let me see. So mainly we working on this technology called photoacoustic imaging. So photoacoustic imaging is based on the photoacoustic transduction from light to the sound. So what is photoacoustic effect? You guys may see this phenomena in our regular life. So in heavy rains, you oftentimes see the lightning. So what happened after the lightning? There's always a thunder follows up. So that is a photoacoustic effects, from light to the sound. So this phenomena has been discovered by Alexander Graham Bell more than 100 years ago. So when Bell developed the telephone, he realized the telephone devices itself are not really expensive, but the cables between two locations have become more expensive and more expensive. So he's, I think, a super smart guy. At that time, he's an innovator. And he realized somehow he can transmit the sound with the other, energy mechanism. Then, he can achieve the wireless communication. So that's why he actually tested whether he can generate sound from the light. So he focused the sunlight onto the really tiny spot on black matters, and then he realized there is sound is coming. Then he published paper, in Science in more than 100 years ago. Then the technology has been around, but it was not really popular. But in 1970, people using material science. Then when laser technology, computer technology, and ultrasound technology become more advanced, it start getting another attention. In early 2000, people try to use this technology for medical imaging. So in conventional ultrasound imaging, you guys may know, the ultrasound transducer generate the acoustic signal and transmit the acoustic signal to the body and receive the echo signal. In photoacoustic, we don't transmit the ultrasound. Instead, we shine in the pulse light. So typically within the safety limit. And then light will be absorbed. It's like in sunny day, if you wear black suit and go outside, your body gets hot because in the black suit, it absorbs the light. The hot means there is a heat generated. We're not talking about a lot of heat here. We're only talking about millikelvin temperature, right? When elastic material that absorb the light, if temperature increase, they start expanding. And then since we are using pulse laser, they're expanding and shrink. They disturbing the medium around there and then start generating acoustic wave. So 1 millikelvin temperature rise is equivalent to 800 Pascal, is strong enough to detect by conventional ultrasound transducer. So pressure amplitude is basically proportional to the multiplication of these four parameters. It's a very simple first order linear equation. So F, if you look at from the left, this is the only equation I have in my slide. So F means optical fluence. So if you dumped more light, you can get very strong acoustic signal. And third parameter called mu A, optical absorption coefficient. This is very important because this parameter is related to wavelength. That means color. Also, this parameter to directly proportional to the concentration of chromophore. So, if concentration increases twice, this mu A increases twice, and then pressure amplitude increases twice. And sigma is called heat conversion efficiency. Any material that absorbs the light is molecule is going to excited from ground state to the excited state. Somehow in excited state, they must release the energy. So one way release the energy to emit another wavelength of light that called the fluorescence. But the other way to release the energy is called non-radiative energy decay. That energy converted to heat. That's what we are measuring in photoacoustics. First parameter called Grunizing coefficient is directly related to the local temperature. So measuring temperature in the body is extremely important. So there is a technique in ultrasound called HIFU, high intensity focused ultrasound. People focus the ultrasound, in tiny spot into the body, and they treat some disease area like cancers or neuromodulation stuffs. And in those technologies, it's extremely important to measure the temperature around there. So currently MRI MRI is widely used to measure the temperature around there. But if you use a photoacoustic technology, also we can map the temperature around the diseased area with some resolution. Then generate acoustic wave propagate through the medium and detected by a conventional ultrasound transducer. Fortunately, ultrasound does not scatter that much in the tissue compared to the light. Also, ultrasound is extremely slow compared to the light. So we can get the time resolved ultrasound signal to form 2D or 3D imaging of the body. So what kind of observer in our body can generate the acoustic signal? Typically in visible and near infrared vision, blood absorb a lot of light. So that means, photoacoustic images can generate very good contrast and high quality imaging from the blood or melanosome, or in some wavelengths, like beyond 1000 nanometer, the fat absorption is increased, so we can image the fat. Also, sometimes we can image the water. So I can summarize what we achieved in the poster over the last several years. So we developed called the photoactivated atomic force microscope. Also, we developed ultra-fast, ultra-wide, label-free, and localized optical resolution photoacoustic microscopy system. This is very similar to confocal microscope. Also, we developed intravascular photoacoustic ultrasound catheter. So intravascular ultrasound catheter is widely used to detect coronary artery disease in clinics. And also we develop whole body small animal imaging scanner like a micro MRI, micro CT, micro PET. Finally, we developed the clinical photoacoustic and ultrasound imaging systems based on the conventional ultrasonic machine. So I can show today, our first clinical trial in thyroid cancer patient. But there are other technology we're also working on. So let me hit first. It's a photoacoustic microscopy system. The technology is very similar to confocal or two-photon microscope. However, two-photon or confocal microscope, they only use the light to excite the molecule, and also they detect the emitted fluorescence light. So excitation also light, emission also light. In photoacoustic excitation part, we need to use light, but emission part, we need to detect ultrasound. So in terms of hardware, somehow we need to combine laser excitation hardware system and acoustic detection hardware system. So this is not easy job, combining optical excitation device and acoustic detector. So people, try to make people try to use some tricks. So two approaches are widely used. It's called opto-ultrasound beam combiner. There is a combiner which can combine and light and sound together. Also, people widely use called ring transducer with a hole in the middle, and then people illuminate lights through the hole, and then they detect the acoustic signal from the other side of the transducer. These two approaches are very popular. Also, there are two modes of the photoacoustic microscopy system, one called the optical resolution, the other called the acoustic resolution. So resolutions are different. At the same time, penetration depths are different. Optical resolution microscopy system, lateral resolution is about 2.5 to the 10 micron, but acoustic resolution system, resolution is become worse to the 80 micron to the 100 micron. But if you look at the penetration depths, optical resolution system is a maximum is about millimeter, 1 millimeter in live animals, 0.5 millimeter in human. But acoustic resolution system, 2.5 millimeter in live animal, 2 millimeter in human, when they use 532 nanometer wavelengths. Both systems are using for human and animal. So what kind of research we can do using the systems? We can monitor tumor angiogenic or anti-angiogenic drug response without any contrast agent. We can monitor tumor progression and regression, some ischemic disease. Also, we can do structural functional neuroimaging, ocular imaging. So it can be widely used in regenerative medicine. So here are some examples. So we developed the system using opto-ultrasound combiner. Now, as I mentioned, blood absorbs a lot of light. So we can see very clear blood vessel network from the live animal. So we acquire vessel imaging from mouse ear and from brain cortex. So typically, there are two photomicroscopes widely used for this purpose, but they need to thin the skull or they need to open the skull. But in our case, we remove the scarf, but skull is intact. So we can see also nice vessel network from the eye or animal's leg. So this kind of system can generate beautiful images, particularly for the vessel network without any contrast agent. The problem, is extremely slow. It's already commercialized, but it took about 30 minutes to sometimes 1 hour to acquire those types of imaging. So people try to expedite imaging speed. So, one way to expedite imaging speed, they use a fast scanning method. So some group, they use a mechanical scanner with a high speed. And then in our case, we use sort of optoacoustic scanning method. So if you learn from the conventional optical imaging people, like a 2-photon confocal microscope, their scanning speed is extremely fast because instead of they move the scanner mechanically, they apply the optical scanning. So optical scanning means, they use the mirror tilt the light. But in our case, unfortunately, we need to scan the light at the same time we need to scan the ultrasound. And also, unfortunately, ultrasound heat propagate in the air. So somehow we need to make a mirror which working in the water environment, and also it reflect the light and sound together. So that's why we develop waterproofing MEMS scanner, or sometimes we use galvanometer scanning, which is working in water environment. Or my colleague at Duke University, they develop hexagon mirror for fast scanning. Or people use micro lens array with a multi-channel data acquisition system, but no, it is expensive because since they use multi-channel data acquisition system. So we developed, 2-axis waterproofing MEMS scanner which reflect and sound together, and also working in water environment. So now we illuminate light through the animal and then generate acoustic wave, again reflected by the MEMS scanner and detected by conventional ultrasound transducer. By tilting the mirror in 2 axes, we can get fast imagings. So here is the movie, how we work. So as I mentioned, it took about 30 minutes to 1 hour to acquire imaging. But in this particular case, we imaged the small animal's brain with intact skull, and then it only take few seconds to get the vascular network in small animal's brain. Also, our colleague in Singapore, they use our machine. In that case, they measured ischemic reperfusion. So initially, they actually place on magnets in the middle, and then once they release the magnet, we see the reperfusion process. Another case here, oops. In this particular case, red means artery and green means vein, so they can see the perfusion process in artery and veins. And also, we relieve the resolution, but we can improve the penetration depth to achieve acoustic resolution microscopy system. Then we can image the entire animal's body. Oops. Yes, we can apply some 3D rendering tools. Using the same system, now we can image the human palm. So for field of view of 3.6 by 8 centimeters, scanning time was 224 seconds. So this imaging speed at this resolution, we can image in a widest field of view for human using this acoustic resolution photoacoustic microscopy system. So we can see clear vascular network from human palm, fingers, and forearm. Also, we can measure human microcirculation. In this particular case, is arterial pulsation using microscopy system. So we actually get the real-time cross-sectional beam mode imaging from human fingers. As you can see, we can measure how signal is changing. That is based on the arterial pulsations. And also in this case, we can measure the perfusion. So initially we block the blood flow. Oops, we block the blood flow by occluding human forearm. And then initially blood flow is blocked. The once cup is removed, we can see new blood vessel is coming. And then also you can quantify the vessel density before with cup and without cup. In C-scan images, we can see new blood vessel without cup. Also, previous imaging systems, B-mode, cross-sectional imaging speed is about between 40 to 100 Hertz. Now we improve the imaging speed beyond 500 Hertz. Then, since imaging speed improved with while maintaining resolution, in this case, we can see RBC directly, and then we can measure the flow information from the RBC movement. By taking advantages of high temporal resolution and high SNR, we also can improve the spatial resolution using called localization image processing method. So basically, we can acquire the multiple images simultaneously, and then we localize the signal. Then conventional photoacoustic microscope resolution is about 5 micron, but once we use localization process, the resolution becomes 1.1 micrometers. Now we can change the optical wavelengths from visible light to the ultraviolet. So if we use ultraviolet, the tissue, DNA and RNA absorb significantly UV light. And then, because the cell nuclei are formed with the DNA and RNA, so we can see cell nuclei structure without any staining. So in conventional operating room, while surgeons do surgery, they excise the tissue, and then they need to confirm whether they excise the entire tumor area. So they send the tissue slice to the histology lab. Initially, they freeze and sectioned and stained, and then they using the conventional and optical microscope they examine. But in our case, since UV light directly absorbed by DNA and RNA, without any freezing, sectioning, and staining, we can image the cell nuclei in photoacoustic microscope. So we can save a lot of times. So we developed the system, as you can see in the video. So our associate place the samples, and then they start the imaging, and then positioning the tissue. Then we can see some signals like cross-sectional imaging, can acquire, and then now we can see entire slice images. So no slicing, no staining, and then we acquire the tissue images. So we compare the image result with the conventional optical microscope after HE staining. So we image formalin fixed paraffin invaded human colon slice. So left one, our ultraviolet photoacoustic microscopy imaging system result. Right one is optical microscopy after HE staining. So these images are very, very correlated, and we can make a boundary between normal and tumorous tissues. Now, we can move on. Previous one is still slice, sectioned slice. But in our case, in this case, we image the human colon cancers. But in this particular case, the tissue samples are unprocessed. It's directly just take out from the patient and we image it. We can see here are normal area, and these are the tumorous regions. Also, we can apply some expansion microscope concepts. So in fluorescence imaging, instead of people improve the resolution of the microscope, they expand the tissue, and using the conventional microscope, they want to see the tiny structure. In photoacoustic, we do same thing, but in our case, we don't need to stain the tissue. So it's a label-free photoacoustic extension microscope. Also, we develop intravascular photoacoustic ultrasonic catheter. So ultrasound catheter is widely used to detect the coronary artery disease. By adding optical fiber into the small catheter distal, and then we excite the light tissue, and then we detect generate acoustic signal using conventional IVUS ultrasound transducer. So we monitor lipid-rich atherosclerotic levels iliac artery. So initially, by doing X-ray angio, we can find where stenosis area. Then we inserted our IVUS catheters in there, and we image that area. So gray shows conventional ultrasound imaging, color show the photoacoustics. So we can get overlaid imaging. So when we are lipid-rich area, we can get strong photoacoustic signal. In other area, we don't see really in the photoacoustic signal. So all these problems actually is coming from when we combine optical excitation tool and acoustic detectors. So this all headache comes from. But if we develop optically transparent ultrasound transducer, all light can penetrate through. Then in that case, seamlessly we can combine many optical and acoustic imaging tools. So as you can see in this slide, we developed the ultrasound transducer which are transparent, optically transparent. It's about 70% transparency in near infrared or visible ranges. So acoustic bandwidth center frequency is about 30 megahertz. So through the system, we fused 4 imaging modality together through this transparent ultrasound transducer: ultrasound imaging, photoacoustic imaging, optical coherence tomography, and fluorescence imaging. So we monitor chemically injured animals' eye. In photoacoustic, we can see before and after the injury, we can monitor cornea neovascularization. In OCT, we can measure the thickness of the cornea. And ultrasound, also we can see some defect area, but relatively deeper region where OCT cannot images. Also, we develop whole body animal scanner using 512 or 1024 hemisphere ultrasound transducers. This case, whole body imaging of small animal from ventral view, and this one is a dorsal view, and this one is a sagittal view. So it's like a micro CT and micro MRI and micro PET. If you zoom up, we can see detailed structure through the animals. Like this structure is the liver. We can see the heart and the intestinal structure. In dorsal view, we can clearly see the kidney and the liver region, and this case is the spleen. Finally, we developed clinical photoacoustic ultrasound imaging scanner. Like this system you typically see in the hospitals, right? This ultrasound system, but we cannot use regular ultrasound imaging system for photoacoustic. The main reason somehow we need to stop sending ultrasound. At the same time, we should be able to get the uh, acoustic signal in raw data form, because all this ultrasound imaging system is based on transmission and reception. At the same time, beamforming is based on the round trip of ultrasound. But we only receive the ultrasound. In that case, our beamforming method should be changed. So this particular system, we can program, our sequence ourselves. So this is kind of special ultrasound imaging systems. So here is real-time graphical user interface. It's like a conventional ultrasound. You can see beam mode ultrasound in grayscale. In colored images, overlay the photoacoustic imaging. So we can change the display mode. Also, in conventional ultrasound, there is a control panel to change all these parameters in real time. We develop user interface in MATLAB base, so we can change these parameters only. Also, we can change some called the time gain compensation. We also control the frequency demodulation. Basically, we can choose where frequency region we want to detect. And also, we can do log compression. Also, there are so many beamforming methods we can choose from the real-time GUI, from real-time GUI. So we develop various beamforming methods in time domain, frequency domain, in numerical algorithm. In time domain, delay and sum, back projection, delay, multiply, and sum, nonlinear piece. These are the widely used. The way I use the yellow is we already implemented this software in real time on the system. The pink one, we code everything in MATLAB. Still, we need to do post image processing. So we are interested to image the human foot. So we develop photoacoustic ultrasound peripheral angiogram of the humans. So here is the movie. There's ultrasound system and laser system, and we just scan without shining the laser first. And then we acquired a contour of the human foot. Then we shine the laser, you can see flash of light here. And in the monitor, typically you can see grayscale of ultrasound imaging and the color, so from photoacoustic and human foot. And then using, once we acquire the multiple 2D slice imaging, then later we can form the 3D imaging of the human foot. So here are the images. So initially we can see general foot contour, and then we can get bone information. It's not based on the X-rays, based on the ultrasound. A deeper, bigger blood vessel we acquire from the ultrasound, and shallow and small blood vessel we acquire from the photoacoustic. These are all 3D. We can render in 3D and then we can merge together. So, and also we apply the, as I said, contour scan. The main reason why we apply the contour scanner, when we do clinical study, human foots are always moving around. So it's difficult to repeat our result. So in order to improve the reproducibility, we apply the contour scanner. In that case, we can measure the hemoglobin concentration, total hemoglobin concentration, hemoglobin oxygen saturation. Although we acquire multiple times over the multiple time period, our imaging result is fairly well maintained. Also, we apply to this technology to image the human thyroid cancers nodule. So ultrasound imaging is gold standard for thyroid cancer diagnosis. So sensitivity is extremely high, it's almost 100%. The issue is specificity. So specificity is extremely low. So there is no problem to find the malignant tumor from ultrasound. The problem, it's difficult to find the benign nodule. So when physician, they look at ultrasound imaging. If small things are suspicious, they always say it's malignant. That's why sensitivity is so high, but specificity is very low. So by adding photoacoustic imaging capability into this clinical flow, maybe we want to improve the specificity. So like a regular ultrasound, we acquire beam mode ultrasound imaging, and then we measure the nodule, and then we turn on the laser and to acquire the hemoglobin oxygen saturation. So initially in ultrasound, they call the ATA guideline, called American Thyroid Association guideline, based on the ultrasound, and then we multiply this one with photoacoustic probability. Then we suggest a new score called ATED. So if the score is above 0.5, we suggest, neither biopsy, otherwise we can maintain. So we improve the imaging specificity is about 93%. Also, we develop, not only we can image the food, we develop handheld scanner like a conventional ultrasonic machine, but it's not 2D handheld scanner, it's a 3D handheld scanner. So we can hold the scanner, image any part of the body. And then in this case, if you turn on the light, there is a flash of light is coming here. And in the images, we can see regular ultrasound is overlaid photoacoustic. By moving the scanner in one direction, automatically we can get localized 3D images. So we imaged, in this case, human cutaneous melanoma. So measuring the depth in melanoma is extremely important, because melanoma is extremely motor once it's metastasized to the other part of the body. So photoacoustic depth we measured, and is highly correlated with the histological result. Also, we're working on some deep learning imaging processing. In this case, we try to correct the speed of sound aberration and also sparse data. So speed of sound in our body is different from the different part of the body. That actually generate a lot of imaging noise. At the same time, if you use a multiple imaging channel, data acquisition channel, imaging system cost is become more expensive or more expensive. If you use less number of the data channel, although you can implement imaging system in cheap manner, but image quality has become worse. So we actually correct these two problems using deep learning tools. So these are conventional photoacoustic imaging, the beam mode photoacoustic imaging at 28 channels RF data, and these are 64 channels RF data. So left bottom is the worst case, because there is a lot of noise in the images. So if you apply the deep learning tools, we can see clear the background in both 128 channels data and 64 channels data. Also, we improve the image quality in hemoglobin oxygen saturation once we apply these deep learning tools. So these are another deep learning imaging processing we are doing for ultrasound using beam mode ultrasound and strain images. The issues, number of data is really tiny in our case, so we apply the transfer learning method. Then we can see about 90% of accuracy and 95% of precision. So also we're working on some multi-channel transfer learning on chest X-ray for screening chest COVID-19 patients between normal pneumonia and COVID-19 using the deep learning method. So you see a lot of 3D movies, it's not a cheap way to do, because you need to buy the software, but we develop our own MATLAB-based 3D rendering software called 3D Phobis. It's working for not only photoacoustic but also all these 3D data you can render in 3D. So these are free for academic use. So if you want to use, so you can email me, I can share the free softwares. Also, we are working on art. So based on the photoacoustic imaging, the artist Hyungi Kim, she drew some flowers in the images we call the cherry blossom. And the other one is called, we acquired this blood vessel imaging from the animal's eye. So we named the eclipse. And also we put this one in Korean Peninsula for peace between North and South Korea. So we have a relatively new journal called Photoacoustics. The impact factor is 5.87. I serve as a section editor for microscopy systems. So if you are interested in anytime, you contact me about the journals. So that's all I prepare for today. And all credit goes to our talented lab members. Thank you so much. Is this about time?
Yes. I'll jump right into the questions that we have in our chat. Thank you for your presentation, Dr. Kim.
Right.
Laura Ange asks, the technique you and your team developed is efficient for all the tissues that the regular technique that is now normally used is as efficient?
It's like as long as the people use ultrasonic machines, right? It's like images the body from the outside, so we can use the technology to images. But certainly, like ultrasound, conventional ultrasound. But certainly, since we are using optical excitation to generate the acoustic signal, somehow penetration depth is limited. So light penetration is always the issue. So like a thyroid cancer, because thyroid is exposed to the outside. So also breast cancer is the breast exposed to the outside. So these two are popular, application, or food, like a diabetic foods. These are the popular area. Also, as I show, we develop catheter. Once you can make everything into the small form factor, and then you can insert into the body like endoscopic catheters. So like ultrasound endoscopy, like ultrasound intravascular catheter. So then, we can use the system in similar manner in that case. But certainly penetration depth is the issue. Also, brain image is difficult because there is a scar. So ultrasound heat propagates through the scar. That's the problem. But people are working on it.
Okay, thank you. Beatriz Diaz asks, optoacoustic scanning is used to reconstruct brain circulation, hand circulation, and others, right? What are other applications of this technique in the future?
So like a breast cancer, thyroid cancer, like a hand scanner, like a foot scanner, endoscopy for gastric intestinal tract, and the intravascular for coronary artery. These are the, I think, is application. Melanoma also.
Okay. Beatriz Barros asks, in which way are the systems you develop different from what's already available in the market?
So market, typically there are a couple of companies developing like selling the some small animal imaging scanner. So well, our small animal imaging scanner, I mean, we use slightly different ultrasound array and to improve the image quality. So whole body small animal imaging result is, on our case, is extremely good. And microscopy system, because that's what we start up the company, is called optical, because we develop microscopy system with really high imaging speed. So I think our imaging speed is the world best. So microscopy system is really good. For clinical system, our clinical photoacoustic imaging system is very similar to the conventional ultrasound. So some company they develop for photoacoustic imaging, but their approach is not like a conventional ultrasound. It's like a special photoacoustic imaging scanner, which we don't like. Now, in our case, a photoacoustic imaging scanner should be very, very compatible to the conventional ultrasound. So our difference is, our clinical system is much more like a conventional ultrasound imaging system.
Okay, thank you for your answer. Eva Anjou asks, in what stage of development is real-time photoacoustic microscopy? When do you think that will be applicable in a clinical set?
Microscopy system, so the issue is it's difficult to find a good clinical application. So as I show, like a human microcirculation we are working on now. And also like histology. images in excise the sample. That's what we are working on. We are doing some clinical study. So, but clinical systems, like as I show, like photoacoustic and ultrasound clinical system, that's going to be commercially available in clinics. I think it's in our case is within 5 years. One system from America, from Biomedical, recently they received the FDA approval for breast cancer. So these are the first FDA approved optoacoustic and ultrasound clinical scanner for breast cancer patients. So that will be available in the market.
Okay. Let me check. Alexandra Pereira asks, can you detect melanoma in situ with high accuracy and specificity?
So we have not studied yet. The issue is in South Korea, not many melanoma patients. So somehow, we need to move the scanner in other countries. So like America, there are many melanoma patients. We need to do more clinical studies. So we don't have any result yet because of number of patients are limited in South Korea.
Okay. An area to explore. Luis Martins asks, you said that your technique can image any part of the body, but what is the deepest dimension that you can penetrate the human skin?
Right. So if you image it from the outside, so from our experience, 5 centimeter, in order to maximum is about 5 centimeter, but we need to average a lot. It takes a lot of time, right?
Mhm.
But within the 3 centimeter, without any averaging, we can get some signal. So as I show the thyroid cancer result, when we select the patient, we select the thyroid should be within 3 centimeter from the surface. So I would think, I'm happy to image about 3 centimeters without any averaging.
Okay.
But good thing for ultrasound, you can press tissue a little bit in order to, shorten your penetration depths.
We have one last question from Inês Gomes. What are the advantages of optoacoustic scanning?
It's compared to the ultrasound, we add a new function like optical contrast. So optical contrast is very sensitive to the many diseases. Like, by measuring optical contrast, we can see hemoglobin concentration or hemoglobin oxygen concentration. These are the hallmark of the cancers. Also any blood vessel related to disease, we can image without any contrast agent, which is another huge benefit compared to the X-ray angiography, MRI angiography, because they need to inject contrast agent.
Okay.
Right?
Yeah, I think that's all from, let me check here. Yeah, I think this is all for questions. Thank you so much,
right.
Kim, once again for sharing with us
All right.
your work. And yeah, I will end this session. Thank you so much.
All right. Thank you so much for your time, invitation.
No,
Bye.
you're welcome. Bye. Aos restantes participantes, boa hora de almoço. Voltamos às 2h.